Good morning, science students. It's Thursday, 5/14/2020. Today, we're going to go through examples of deposition. So, yesterday we talked about how rock breaks down through processes called weathering, and then erosion moves stuff around, moves the little pieces and sediments around. But eventually they end up in some new location. That's going to be deposition. And when they're deposited in those new locations, certain landforms are created that we can see around us. So we're going to go through several types of landforms created by deposition, and I would want you to be able to name them and describe them. We're going to have a very basic description of how metamorphic rocks form. I'm not going to spend much time on metamorphic rocks. And then we're going to look at some examples of how does one rock change into another. And I would want you to be able to explain that. So, deposition refers to eroded material, sediments, getting dropped in a new location. Deposited. They are deposited. They are dropped in a new location. All right, I know the writing may be a little bit tough to read, but I'll read through it. So my first example of a landform created by deposition is called a floodplain. So I'll come to reading that in a little bit, but let's imagine here's a river. Here's the banks of the river. Now occasionally we get heavy rains, storms, hurricanes, snowmelt, and this river floods. And when the river floods, it's usually flowing really fast, and so it's carrying a lot of sediment with it, erosion. But if it overflows its banks, now that water flows out into this really wide range here over all this terrain, and it slows down. It's not just locked up in this channel anymore, so it goes out here and it slows down. And when it slows down, it drops its sediment. And so this area alongside the river, which is often quite flat, this is called a floodplain, tends to be great farmland because all that sediment and material that comes down gets dropped and it adds nutrients to this soil. The problem is, this is an area that's also prone to flooding. So, you know, it's some great soil for raising crops, but it has its other challenges. All right, so what does it say? When the floodwaters spill over the banks into a wider area, the water slows and drops its sediments. One more time. When the floodwaters spill over the banks into a wider area, the water slows and drops its sediments. And where it's dropping its sediment is a floodplain. So here's a picture of a river that looks like it is flooding. And you can see if it raises a little bit more, we've got all this relatively flat area alongside. So when this river floods and the water goes over here, some of the sediments get dropped into that flat zone. You can see this looks like farmland. Okay, next one. A delta. Okay, a delta. So I have here kind of a rough sketch of the United States. And here's roughly the Mississippi River. So let's imagine we get heavy rains or something, and the Mississippi River is possibly flooding a bit, and it's carrying sediment. So I drew a little brown in there that the river is carrying sediment. Well, when that river gets to the ocean, you have a flowing body of water moving into something that's kind of still. And so the water slows down when it gets here. And when it slows down, it can't carry as much sediment. And so the sediment, you know, possibly soil from Edgar, Wisconsin, ends up getting dropped into the Gulf of Mexico right down here. And that over time builds up a landform. And it drops all this mud and sediment, and the river keeps looking for new ways to try to work its way through, and you get what's called a delta. And it's called a delta because oftentimes it has kind of a triangular shape to it. So let me read these words here. A river or stream flows into a large body of water. It slows down and drops its sediment load, this forms a river delta. The river or stream flows into a larger body of water. When it does so, it slows down, drops its sediment, and forms a delta. So here's a picture of a river delta. And you see that the river, as it's getting close here, it gets broken into all sorts of little channels that are constantly changing because, you know, new material gets dropped and then the water tries to work its way around it and gets split up into things. And we've got kind of this triangular shape that takes place. That's a river delta. The next one is rather similar to a river delta, but it's on land. Okay, and it's called an alluvial fan. Now there's a word you probably haven't heard much before. Alluvial, A-L-L-U-V-I-A-L. An alluvial fan. So it's like a delta. You have a fast-moving stream, typically coming down maybe the mountains, and it flows onto, it's going down a hill, and then it flows onto flatter ground. And when it flows onto flatter ground, it slows down. When it slows down, it can't carry as much sediment, and it drops its sediment. So here's a picture. You can see this, you know, here we got some mountains, and there's this, you know, this notch here in the mountains where water could come flowing down, and that water would be moving really fast. But then it gets to the bottom, and it's like all of a sudden it's slowed down. It's not going downhill so much anymore. So it drops its material. And so we have this kind of mound of material that is at the bottom of the mountain. That's called an alluvial fan. Dunes. That word was hard to read, so I redid it. All right, so now we're talking about wind. And wind blows sand. And what happens is as the wind's blowing, it picks up little particles of sand, and it might lift over a little ridge, and then it drops things. And so what always happens is these dunes are shifting. So sand's getting blown up off this backside here, and, well, maybe this is the front side, this is where the wind's hitting, and the sand flows over top. When we get to this side, that's sheltered from the wind, the sand drops here. And so these things keep shifting all the time. And it's a lot like the snow drifting process that we see in winter. In fact, it's really exactly like the snow drifting process. Those are called dunes. And here's a picture of some sand dunes. Oh, back to this. You notice the dunes always have one side that's smoother and then one side that's steeper. This tells you where the predominant wind direction comes from, because what's going to happen is where the wind is coming, that's where it's going to pick up the sand, and then it drops it behind. This side where the wind's hitting gets sloped more, or more gradual. Beaches, sandbars, and barrier islands all result from sand getting shifted around and deposited. Okay? So what do they look like? Well, I think you've at least seen pictures of beaches. That looks like a nice place to be. I wouldn't mind spending some time right there today. Here's some sandbars. Here's a barrier island. Now, I don't know what the specific definition is, because it really kind of seems like a barrier island is just kind of a bigger version of a sandbar. These are all temporary landforms. All of these things get changed all the time. Storms come in and wash out beach sand. One of my favorite places on earth is a spot on the island of Bonaire where I go scuba diving. And it's just this little bit of sandy beach along the shoreline. And it's because it's fairly smooth sand, it's one of the easiest places to get into the ocean on the whole island, I think. Unless you're actually at a dock where you have steps to get in. So I've done dives at that particular location many dozens of times over the last years. Twice, I think it is, that my wife and I showed up there and there was no sand. The waves had washed the sand out. Later on, they brought the sand back in. Sand in all its forms is a temporary thing. These barrier islands, now here's the sand that's built up, and if it's a little bit more permanent, it gets some vegetation on it, which helps anchor the sand and hold it in place. Think about what a service that does when storms come in and waves come in. It breaks the waves before they hit the main shoreline. The problem is, and I don't know if you can tell in this picture, but somebody went and built a city on the sandbar. So now when the storm comes in, that city is right in direct way of all the waves and storm surge. It's probably not one of the better decisions we humans make, is to build for us, a seemingly permanent city on a landform that's temporary. All right, a moraine is a glacial feature. So glacier is this mass of snow and ice, and so heavy, so it pushes, it moves forward, and as it's moving forward, it plows up the ground and debris and rocks in front of it, and it can be like a bulldozer pushing a pile of rocks. Well, what if conditions change and that glacier now starts to retreat? It doesn't pull the rocks with it again, so the rocks and debris stay left behind. Now, that debris is called till, glacial till. And so the pile that's left behind when the glacier recedes is called a moraine. M-O-R-A-I-N-E. Here's my drawing. I got a glacier. Here's this mass of snow and ice, and it's plowing forward over these rocks, and it's pushing this pile of glacial till in front of it. If that glacier now starts to melt and recede, that pile is going to be left there. That'll be the moraine. I was looking for pictures, and I really like this one that I found. You can see here's a valley glacier, this river of snow and ice that was flowing down here. And you can see at some point in time, it got this far out. But now it's receded a little bit, but look at that pile of debris that's been left where the glacier had at one point been. That's a moraine. Now we're going to get to chemical deposition. Let's say we have stuff that's dissolved in water. Caves are great for this stuff. We get stalactites, stalagmites, and columns. So let's imagine here's a cave, and I've got rock up here, and water comes seeping through the rock, and the water contains minerals, and we get a drip right here. And when that drip leaves, it leaves behind just this ever tiniest little bit of mineral. And so that, over time, lots and lots and lots of drips is going to build up a stalactite. Now, I'm going to read this to you because you probably can't read it. Stalactite, tapering, icicle-like structure hanging from the roof of a cave. It's made of calcium salts, calcium compounds. Now, how do you remember which one's which? Stalactites hang tight from the ceiling. Now, where that drip hits the floor, it also starts building up material. So we get this tapering structure sticking upward from the floor of the cave. That's called the stalagmite. Stalactites hang tight, stalagmites grow up from the floor. If you give it a long enough period of time, the stalactites and the stalagmites might meet, and now we have a column. So a column is this whole vertical pillar of calcium salts that we see in caves. So here's a picture in a cave. We've got stalactites hanging from the ceiling. We've got stalagmites sticking up from the floor. And here's one where they've joined together and we've got a column. All right. A long, long time ago, in a planet that you're living on, the oceans actually had a lot of dissolved iron in them. And then some of the earliest bacteria and algae started giving off oxygen, and our oceans rusted. The oxygen that those organisms were giving off combined with the iron that was in the oceans, and the iron oxide precipitated out onto the seafloor. So on my picture, I've got my ocean, and my little green dots here, that's living things, algae and plants and things, okay? And I've got iron that was dissolved in the water. And so as the algae produces oxygen, it combined with the iron, that made a solid compound that settled to the bottom. Fe3O4 and Fe2O3 are two of the compounds that are formed. Fe, sounds funny, but it's actually the symbol for iron. Comes from the old Latin word ferrum. Okay, so we get these iron oxide compounds on the floor. Well, the climate changes. This sea maybe goes away, and this slab underneath here gets compressed together, turns into solid rock. Maybe some years later, it's uplifted and ends up in northern Wisconsin. And you find these banded iron formations where there's these layers of sediment from a long, long, long time ago, billions of years, that have these layers of iron compounds. And boy, if you're going to run an iron mine, that's some high quality ore right there. And we have some of these formations in Wisconsin. Northern Peninsula of Michigan. Think about some of the names we have. Iron Mountain, Michigan, Iron River. I think we have Iron County in Wisconsin. All right, so those were all deposition forms. Now I'm going to go a little bit into metamorphic rocks. So metamorphic rocks, we already had that brief intro a couple days ago. This is where you take a rock that's already existing and you apply heat and pressure deep in the earth, and you change the structure of that rock. Okay, so two of the keys: heat and pressure, extreme heat and pressure, but we're not melting it, because if we're melting it, we'd be making magma, and then it would cool into igneous rock. We're not melting it, we're just changing it to something else. Metamorphosis means to change to something else. So there's two varieties of metamorphism that I'll hit. One is regional. So let's imagine this whole range of rock is hot and under pressure. So there's this big region here that's hot enough and being squeezed enough that the rock here starts to change its composition and or structure. That's called regional metamorphism because the whole region is changing. But something else that happens, sometimes you have within our rock, we have a magma chamber. Okay, it's a volcanic region. We have a magma chamber, and it's just the rock that's alongside the magma chamber that has enough heat. It's under pressure from the rock from the sides, but it's hot enough near that magma chamber that undergoes. So we just have kind of this area right around the magma chamber that is changed. That's called contact metamorphism because it's in contact with that big heat source. Again, the magma, that's melted, that could turn into igneous rock. We're talking alongside the magma where the rock changes without melting. Here's an example where they show the sample of rock. So shale is a sedimentary rock. And if you apply heat and pressure over a long period of time, shale goes through some changes and turns into a rock that's called slate. And if it goes under more heat and pressure changes, it turns into something called phyllite. I'm not sure if I'm pronouncing that correctly. If it undergoes more changes, it becomes schist. And if it undergoes more changes, it becomes something called gneiss. All came from the same basic rock structure. So metamorphism, this is a metamorphic rock. So is this. So one metamorphic rock can be further metamorphed into a different rock. And it can be further metamorphed into a different rock, Okay? Heat and pressure. So, this is a diagram of the rock cycle that I had shared with you a couple days ago. And I just want to throw you through a couple of examples. So I want you to think, how could you change a sedimentary rock into an igneous rock? This diagram tells you we got to find a path where the arrows point from here to there. Okay? Now, maybe it's easier to find backwards. These are all arrows coming out of igneous, so let's go to arrow. All right, to get to igneous rock, we got to cool and crystallize some magma. And then how do we get to magma? Oh, we could have melting. So, according to this diagram, if I took a sedimentary rock and apply enough heat to melt it into magma, then that magma could cool and crystallize into new igneous rocks. Where do you think that heat happens? Probably down deep in the earth. Okay? A lot of this, the heat from melting, is going to happen down deep in the earth. The heat and pressure for metamorphism is going to happen down deep in the earth. The weathering and erosion, that typically happens up on the surface of the earth. So rocks form and they get lifted up and they get buried and they get lifted up and they get buried. The earth's surface changes over time. Okay? Let's talk about how could we take a metamorphic rock and change it into a sedimentary rock. And again, I'm going to start with the sedimentary and work backwards. Sedimentary rock would work if we were compacting and cementing together sediments. How do we get sediments? From weathering and erosion. So, could we take metamorphic rock, expose it at the surface so that it weathers, breaks down, gets moved around, erosion, gets deposited into a new place, a pile of sediments, and then those sediments are compacted and cemented together? Sure. Could we change igneous rock into sedimentary rock? Sure. We could weather and erode the igneous rock, sediments, compact them together, sedimentary. Could we take sedimentary rocks and turn them into other sedimentary rocks? Sure. The sedimentary rocks could be weathered and eroded. In fact, sedimentary rocks erode easier than other things. And they could turn into new sediments to form new rocks. Happens all the time. So any one of these rocks, rock types, could turn into any one of the other rock types. And you just have to follow the arrows. And I'll be honest, I'm a little bit proud of this diagram. I redid this year, and I think this is a better diagram than I've ever made before. Nice fancy arrows. So use it. Okay? Use it to follow along and figure out how rocks can change from one to another. And that wraps up our unit on rock cycles. I'll give you an apology. I really keep thinking about trying to make a song parody. There's an old song from the 1980s from a hair band called Twisted Sister, and the song's called I Wanna Rock. And I'd like to write a parody of I Wanna Rock about the rock cycle. I've only ever gotten just a couple of lines kind of stuck in my head, and it takes a lot of time and effort to sit down and write a parody. I've tried it before. So all I got is, I wanna rock! Okay, that's it. And that squeaked out, so sorry. All right, sometimes Mr. Up gets a little loopy, but you probably enjoy that. Take care. See you soon.